We already know that we can add matrices together and multiply them by real numbers. Now let's see another operation, multiplication. Now we're not just doing this for fun. It turns out that multiplication is going to make it even easier to solve linear systems. But before getting into the nitty-gritty details, I want to introduce a tool that will help us perform the computations. So let's suppose that I give you two vectors, x which is a row vector and y which is a column vector. And an important make before we go on is that both vectors must have exactly the same number of elements. And if they do have the same number of elements, we can define their dot product, denoted by using a little dot between the vectors, as follows. So here we're multiplying the vectors component-wise and adding them together. Now we're often pretty sloppy about dot products. We will use the dot product between two column vectors, two row vectors, a row and a column. And here I've chosen a row and a column in this order for a particular reason, and we'll see that reason at the end of the video. So as a quick example, here's two vectors. And we will multiply the first elements together and add to that the product of the second elements, and finally also the product of the third. And it's a simple matter to add these together and we get -1. So importantly, keep in mind that the dot product of two vectors is not a vector, but rather a real number. Okay, so now we're not going to work a lot with dot products explicitly, but rather we're going to use them as tools to help us compute matrix products. So to that end, suppose A is an m by k matrix and B is a k by n matrix. And I want you to pay close attention here to the dimensions of the matrices. Note that they have a k in common. So in that case, we define their product AB to be the m by n matrix whose elements look like this. And remember that this means that we're looking at the ith row and jth column of the matrix AB. And this is probably a bit scary. And moreover, it looks like a lot of work to compute a single element, but hopefully you also see that the equation above looks a lot like a dot product. So let's change our view of the problem. If we write A in terms of its rows, so that there are m rows, each of which is a 1 by k row vector, and B in terms of its columns, so that there are n columns, each of which is k by 1. If we set up the problem like this, then the matrix is just a big old matrix of dot products. All right, so while I'm filling all of this in, I want to point out that the element in the ith row and jth column of AB is the dot product of the ith row of A and the jth column of B. And so this is going to make it a lot easier to keep track of our dot products. All right, let's write down some matrices and practice multiplying them together. And before going further, let's discuss the dimensions. So according to our definition, the inside dimension of the matrices has to match up. And in this case, the inside dimension is 3. So we are allowed to do this multiplication. The outside dimensions then combine to give us the dimensions of the product. So in this case, our answer is going to be 2 by 1. So I'm going to write out these matrices again, and while I'm doing that, let's note that none of these matrices are the same size. We got a 2 by 3, a 3 by 1, a 2 by 1, and in general, sizes are not going to be preserved across matrix multiplication. All right. So we're going to compute the 1, 1 element of this product. That means we take the dot product of the first row and first column. And if we do that, we get this long string of numbers, which we'll evaluate in a second. The next element is in row 2, column 1, so we dot the second row and first column to get this. And at this point, we're pretty much done. We're just going to simplify everything out, and that's going to give us our 2 by 1 answer right here. Great. Let's do a slightly more complicated example this time. So here is a 3 by 3 matrix and a 3 by 2 matrix. Once again, we notice that our inside dimensions match up, so we can legally perform this multiplication. And our resulting matrix will be a 3 by 2 matrix. So here, the resulting matrix is the same size as one of its factors, namely 3 by 2, and that's because the other matrix is a square matrix. It's 3 by 3. Now, you don't need to do this, but to help us out, I'm going to label the columns and rows of the resulting matrix. Here we're working on row 1, column 1 of the product, so we dot together row 1 of the left matrix and column 1 of the right matrix, and doing that is going to give us -6. Moving to row 2, column 1 of the product, we look at row 2 and column 1 of the factors, and that gives us +6. And so on for the rest of this column. Now, here we're looking at row 1, column 2, so we dot together row 1 and column 2 to get -4. And if you haven't done so already, pause the video now and try to finish the last 2 elements yourself. And there we go, all done. So to finish off, I mentioned that we would define the dot product as being between a row vector and a column vector. And so why did I do this? Well, the dot product is an example of a matrix product. So let's set up our dot product like we did before with our row vector x and our column vector y. And as matrices, note that our inner dimensions do match. So we can multiply these together, and moreover, the result is going to be a 1-by-1 matrix, which is just indistinguishable from a real number. So if we do the multiplication, the answer we get is this, which is just exactly the dot product. And there we have it. So now we can multiply matrices.